Welcome in, everybody. Warm welcome. Thank you for being here. Glad you could be here. You should be glad you can be here. Go ahead and get yourself ready with a pencil or a pen and a notebook. Really whatever you choose to write with is fine. This is math from the void. Math coming at you, pretty much out of nowhere. Today we have a problem from the 1999 AP Calculus exam. This question was on the AB as well as the BC exam. Don't feel tempted to draw this out if you don't want to, although you can. You're welcome to take the time to draw this out, and it won't count towards your time solving the problem because this would have been provided for you. But this graph is consisting of 3 line segments. We have an x-intercept of -2, 0. Then it crosses through. Looks like it's a little bit above 2.5, so it shouldn't be right at 2.5. But we have another point for the segment at 1, 4. And then the second line segment goes from 1, 4 to 2, 1, goes down there. The third and final segment goes from 2, 1 to 4, -1, and it does seem to pass right through x equals 3. So give yourself about, maybe 12 minutes or so to work on this problem. And then when you're ready, you can come on back and see how we do it here. Sound good? Okay, let's get started then. The graph of the function f is given, consisting of 3 line segments, and g of x is a function defined as the integral from 1 to x of f of t dt. So basically, from 1 to some x value. Remember, if we have to go backwards, we have to consider that as a negative value for the integral. Just keep that in mind. Let's get started with part A. Compute g of 4 and g of -2. So that's going to be really simple. And we see some really nice line segments, so it's not going to be too difficult. Let's see, g of 4. First of all, g of 4, by definition, is going to be the integral from 1 to 4 of f of x dx. Okay, so this is basically just the integral, the area under the curve from here to here. Now, if you notice, that's going to go all the way over here, and then we have some negative space as well. If you notice something very precise, it's that after 2, the area from 2 to 3 is going to sort of cancel out with the area from 3 to 4. So really, we can say that this is the equivalent of the integral from 1 to 2, which is just the area of a trapezoid. So that's going to be 1/2 base 1, which is 4, plus base 2, which is 1, and then times the height, which is sort of like the delta x here. That's just 1. So this trapezoid's kind of standing on its side. Okay, and that's simply going to give us 5/2 as the value of the integral. So there we have it, 5/2. Now, when it comes to g of -2, this is where we have to be a little bit careful because all of this area is going to be counted sort of negatively. So if we go from 1 to -2, this is going to be equivalent to negative integral from -2 to 1 f of x dx. So let's try to figure out what that is. Well, that looks like it's just a simple triangle. Yeah, it is. So from -2 to 1, we just have a triangle, the area of which is 1/2 base, which is from -2 to 1, that's 3, times the height of 4, so we just have -6. Very straightforward use of the definition of the function, keeping in mind that for any x values which are less than 1, we'll have to kind of flip the integral using the properties of integrals, making sure that the bottom limit, the lower limit, is truly the lower number, the lower value. Okay, let's look at part B now. Find the instantaneous rate of change of g with respect to x at x equals 1. So we're going to use the fundamental theorem of calculus here because we need to take the derivative. We need to take the derivative of an integral because the derivative of g, I guess I'm kind of writing into the question C, is just the derivative of an integral from 1 to x f of t dt. Okay, so if we want to take the derivative of an integral, let's do that carefully. Let's instead say that g prime of x is equal to the derivative of capital F of x minus capital F of 1. This is where f is an antiderivative of little f. Okay, and if we take the derivative of that, then we're just going to end up with little f of x. Okay, it's not bad. So g prime at this point, x equals 1, is simply going to be f of 1. And we can just look at the graph for that. We have that value of 4. Very simple. So at that moment, x equals 1, the area of, sort of like the area, underneath the curve is changing at that moment by 4, because if we were to like make a rectangle at that height, we'd be adding an area of 4. Okay, pretty easy. So just remember that the second part of the fundamental theorem of calculus, it basically says that a derivative and an integral cancel each other out, but it's safer to write this because it's possible we have to do some chain rule thing, or if the limits are not just simple expressions like 1 and x. Yeah. Let's move on to part C. Find the absolute minimum. So whenever they say absolute minimum, they oftentimes require an interval to be given, a closed interval. And so to consider this absolute minimum, we have to check either endpoints, I'll write it down here. We have to check endpoints or critical points. And we're asked about the absolute minimum of g. So we need to look at endpoints, meaning g of -2, which we've already sort of calculated. That was -6. We did that in part A. And also g of 4, which we also calculated in part A, which is 5/2. So we have 4, 5/2. So far as minimums go, it's looking like -6 is pretty minimal. Now, just to give you an idea of how g changes, we start off at -6 over here, and as we go to the right, we're adding more area. So it's increasing, until we get here to 0, and then it finally starts decreasing. So I really have no reason to believe that the minimum value is lower than -6. The values are going to increase quite a lot, and then at some point they'll go back down a little bit, but it's only going to go down enough to cancel out how much was gained in the portion from 2 to 3. So if we look for critical points, we're looking for where g prime is 0, which basically just means f of x is 0. And that's going to be when x equals 0 and when x equals 3. But of course, the values here are going to be much greater than -6. So if I were working on this, I would kind of be done there. I would stop there. And I would say that x equals, oh, sorry, not x equals 0, x equals -2. So x equals -2 is obviously one of these potential points, and x equals 3 this is going to be a relative maximum. And that's because G prime, a relative maximum of G, and then that's because G prime, which is just f of x, goes from positive to negative at x equals 3. So that's going to be a relative maximum. We don't even really have to calculate it. I'll do it really quickly just because it's a really easy definition. It's just the integral from 1 to 3, which is just going to be the integral from 1 to 2 plus the integral from 2 to 3, which is a little triangle. So we have 5 halves, right? We already determined that that's the value from 1 to 2. And then plus this little tiny triangle, which is 1/2 base of 1, height of 1, so total of 6 halves or 3. That's definitely not the minimum value, right? So the absolute minimum of G on the interval from -2 to 4, is -6, and this is at x equals -2. Okay, really good there. Really good progress we're making. Remember that for an absolute maximum or minimum, we're checking the endpoints and the critical points. Those are the candidates for potential maximums and minimums. The second derivative of G is not defined at x equals 1 and x equals 2. We can verify that. Let's verify that now so we see what they're talking about. The derivative of G is f. That's the graph. The second derivative of G is therefore the first derivative of f, which is the slope of the graph. And as you can see, there's no slope here at x equals 1 and here at x equals 2. We have these sharp corners. So the question is, how many of these values are x-coordinates of points of inflection? Well, in order for something to be a point of inflection, and the question is how many, in order for something to be a point of inflection, that means the second derivative changes sign. So again, G double prime equals f prime. So we want to look for moments where G double prime goes from positive to negative. In other words, when f prime goes from positive to negative. So from when the slope of this graph goes positive, like it goes, to negative, and then it continues to go negative. It does not switch there. So we only have one point. So for part D, we can say G double prime, which equals f prime. First, let's say this. G has a point of inflection, POI, when G double prime, which is f prime, changes sign. It's asking how many of these x values, x equals 1 and x equals 2, have that change. So we'll say f prime changes sign at x equals 1, but not x equals 2. Therefore, G has a point of inflection only at x equals 1. And we don't have to find what the point of inflection is. We could find out what the G of 1 is. G of 1 is just 0 because the integral from 1 to 1 is just 0. And if you notice, f prime tells us how much the value of f is changing. F is still a positive here. So even though the derivative kind of changes a little bit, that just means that the amount of area that's accumulating is different, but it's still positive accumulation of area. Yeah, we're still adding more area. Whereas when we hit x equals 1, we were adding a lot of area, and now we're starting to add, we're still adding area, but we're adding less. Okay, so concepts that we covered here were the fundamental theorem of calculus, conditions for finding an absolute max or minimum, and then even just analyzing the derivative of the derivative, which is just the slope of the given graph, in order to make some conclusions about the integral and points of inflection of this function g. But I think that's enough blab out of me. Hope you guys learned something here, and I will catch you next time in the void.